What do you mean?
Kind of like explaining it to me,
Mm-hmm.
and they shared a Google Doc with each other, and they're both taking notes at the same time. Like,
Yes.
are we just like kind of writing down what you're saying and like some key points and stuff? Or
Well, you're welcome to join any other lecture note group. I didn't assign them or anything like that. I just said if people want to do it, you're like one person would scribe and another person wouldn't. You do have to make a progress report and then share that with me.
Okay.
Did you see that in the slides? Okay.
I'm not sure how to structure it yet, but I was just gonna ask for like how.
Sure. Yeah. Feel free to ask them if you can jump in their notes. You know, I recommend that, you know, if someone wants to keep notes simultaneously, they can do that, but they can also just like type comments in.
Okay, sounds good.
Cool.
Thank you.
Okay, folks, so I'm going to start off by pointing your attention to the syllabus, which I know you all follow quite closely.
Oh, yeah.
Including updates to the syllabus. So, religiously every morning when you wake up, right? So this is these are going to be our help sessions. There's Astro 2300 ones in here too. If you show up and there's no students from Astro 2300, you just ask a question. I'll be there. They're in PS 103. That's the computer lab. Not this one, the other one over there. And it's half an hour long, but you know me, I like to talk. So I have a whole hour blocked off, but I'll only commit to being there for 30 minutes if no one's there. Then I'll leave. Okay, questions? Cool. We have a lot of stuff to get through, and I may have bitten off more than I can chew, thinking that we could do a chapter a week. So we'll see. I'm also going to attempt here. I have a little what is this called? AirPod in. This is going to be my microphone. If it dies halfway through, that's expected. And we'll see if it gives us a better quality when I'm talking, because you know I like to walk around the classroom. Okay, so what's this? Ooh. Weather balloons? Weather balloons, yeah, good. What else do you see? We see clouds. Clouds? The sun? The sun, yeah, that's good. Sun. That's good. A sun. A sun. It's not clear. Is this a real picture or what? Relatively real. Okay. Okay. Yeah, who would take the photo?
Another.
A drone. A drone. Everyone's familiar with drones now. They can do anything. So this is not a real photo, because this is a mock-up of what this will be. This will be like the cheapest way to get into space. Instead of going to suborbital space, you just get in a big old balloon and you float to the edge of space. And we're going to talk about how balloons float today, which I think you all know very intuitively. We're going to understand physically why it's actually doing this. Why are the clouds like flat on the top? Yeah.
I have a question, not related.
Yeah.
Sorry. So the notebook that you wanted us to put like our last name and stuff for.
Yeah.
What is that exactly for?
The progress reports?
Yes.
That is a progress report.
What do we write on it?
Whatever you want. You can write what you thought about the class that day. You can write about how you felt about the homework. You can write anything you want. It's you taking track your progress in the class.
Oh, so I can take notes.
You can take notes in it. You can do anything you want in that. Within reason. The idea being that when we have our 5-week check-in, you'll come to me with your progress report. I'll be following it the whole time. And if it's empty, I'll have nothing to base our conversation off of, except for what I've seen in class. If it's at least filled with a little bit of words, I'll be like, oh, this person gave a little bit of thought. They're very detailed, and you feel like you put some nice summary into every week or every class, however you want to do it. If you want to do it right at the end of 5 weeks, this is what I learned. Great. It's a progress report. Okay. And there's no like requirements for page length, for depth, be bullet points. I don't care. Whatever your form of learning is what I want to see. Okay. Why do the clouds end here?
Atmosphere stratified.
Atmosphere stratified. Okay, we're gonna get back to that in a little bit. It definitely is, but why do they end here? Yeah, that's what stratified means. So you're saying the right thing. You're right. You're both right. Same thing, same concepts. But why does it end here?
Can't keep floating.
Why can't it keep floating up?
They're less than.
Yeah. Yeah.
Might be wrong, but like gravity?
Yeah, yeah. What is gravity doing to these? Pulling what?
Water.
Down. So these are,
Water.
yeah, water molecules that are heavy. They can't float forever. This thing here can float forever because we put. No. What's lighter than air? Helium. Helium and hydrogen are lighter than air, so they go up. Yeah.
Are the clouds looking at equilibrium of like gravity?
Yeah, I guess we're about to find out. Smart. Aldo's got it already. All right, he might have done the reading. So let's just recap what we have here. We talked about this idea of what is a fluid, right? Because how many phases of matter there are? Two. Right? We don't subscribe to this 4 or 20 bullshit. It's just 2, and it's mostly can I stand on it? And so we're talking about the Knudsen number, and that means. What is this used for? Correct. And if it's smaller than 1, it's a what?
Terrestrial?
We're looking for either if it's a fluid or non-fluid.
It's fluid.
If it's less than 1, much less than 1, it's a fluid. Why? Because of course here we were talking about the little L being how long it takes for a particle in the fluid, quote unquote, to bump into another particle. And we're comparing that to a length scale of interest. How the heck do we define that stuff? Well, we'll need something called the Maxwell distribution. Raise your hand if you've ever heard of that. Okay, cool. In this class, we're going to use lots of different letters. As I mentioned before, I'm going to do my best to differentiate them. You'll see little v's, you'll see big V's. When I draw them, they will look similar. Okay, so ask for clarification. Little v's are going to represent all possible velocity states, whereas u represents the bulk velocity, especially if it's a large u. And if it's a large curly u, that's going to be energy. So, all right, get used to that. So what does the Maxwell distribution look like? Well, if you have your book open, you'll see that it has some fun parts to it. Write it down. So, can anyone describe what it is? Heard a lot of people raise their hand and they say, yes, I've heard of it. And no one wants to tell me what it is. Maxwell distribution?
Thermodynamics, right?
Yes, we did see it in thermodynamics. What does it mean?
The number of molecules.
What's that?
The number of molecules between your initial velocity and the velocity of the
In the reading, or do you understand them?
It's what I took notes on.
Okay. Okay. Good. So that's the right way to think about it. So in fact, finish this and then we'll talk about it. All right. So it's a velocity distribution. Let's look at those words. We know what velocity means. Right? Velocity is speed and direction. Right? And a distribution means how it's distributed. And how much of it is in which. So we talk about income distribution, right? Probably peaked towards me and maybe less towards you. Get older, hopefully that flattens out, right? So how does a velocity distribution look in a fluid? What would this look like? Anyone have an intuitive sense for this? Okay, so Isabel did a nice little hand gesture. Can you repeat that for the class? Why does it go up and down? Yeah, and how would you see that here? I want you to look at this map and immediately have an intuitive feeling for it. Because what? It's cube. Where's the cube? Okay, so let me ask you a question. What's in here? So we have M. What's that? Mass. And what's KBT? Like an energy, right? Okay, does this have a variable in it? No. Okay, so this is garbage. So I could call that beta. What's that? E to the stuff what? E to the stuff squared. Oh. E to the stuff squared. Here, this one too, I could call this whatever I want. Okay? So it's E to the stuff squared. And in fact, the velocity distribution, it's like that. Oh, what does that thing look like? Like a what? Like a Gaussian, right? So importantly, there's a minus sign here. E to the stuff minus squared is a Gaussian. Now there are some little modifications to it. But the Boltzmann distribution says that there's a peak value and there's some variability around it. Yeah.
What is the function called?
This is the Maxwell distribution. That's this one right here, equation 1.1. Okay, and that's what it looks like. So what you're looking at here in velocity space, these are different choices for the width. So this one is peaked at I don't know, 0.25 or something. And this one's peaked over at 7. Okay. Okay. So this tells us if we look in a little box of fluid, how many particles there are moving with what velocity. You can take this value and you can do fun things on it called moments. So moment is not like what we're experiencing right now. It's like when you take an integral with respect to something. Have you ever seen this in other classes before? Like the zeroth moment? Okay. So imagine that that's the velocity distribution. We would define n. As that integral, and that's over all space. And what does that say?
Just pointing in all directions, X, Y, Z.
Yeah, just pointing in all directions, X, Y, Z. Remember what this formula means? What does F mean here? It's the likelihood of finding some number of particles with the velocity v. So if my integral goes over all v in all three directions, what do I end up with? Particles of that velocity or particles of all velocities? So by definition, this goes from minus infinity to positive infinity, and it samples how many particles are at 20, how many particles are at minus 300, how many particles are at 0, and it begins to add them up. That's what the integral is, right? That is just a function that tells me there's 6 particles with speed 2.6 kilometers per second, right? Or the likelihood that I have that many. So this integral, by definition, if I do it over all of these variables, has to give me back the total number of particles. Great. That's called the zeroth moment. And that's in your book as well. If you take the first moment, it's pretty straightforward here. It's just a fun way to say you're going to multiply that velocity distribution by the velocity. That's going to give you the mean molecular speed. Okay. Why do we care about the mean molecular speed? Well, because we need it in order to estimate the mean free path. The mean free path is what we're using in order to determine the average length before you bump into another particle. Remember that we're thinking about this fluid as like a box. There's billiard balls all in it. So you have to know how many billiard balls there are, how fast they're moving, and what average direction they're moving. Now, if the box is itself not moving, what's the total box's average velocity? 0. Has to be 0. Otherwise, the box of fluid would move. Right? If there is a general motion to the fluid that will come out of the average. Okay,
The triple integral is just used to get how many particles inside?
all of them. I didn't put the bounds here, but this is equation just under 1.1. It shows the triple integral done with each dv properly. Memorizing the math here is not the important part. Understanding the math is. Okay. Okay. So we're going to start with thinking still about particles, and I promise we'll get to fun stuff. But first we have to talk about molecular transport. Okay, what the fuck does that mean? Yeah, diffusion, great. Okay, good. All right, so molecular transport refers to the movement of molecules. So you take a big old box, and on one side you put the hydrogen atoms, and on the other side you put oxygen atoms. And what happens? Okay, yeah, hand motion. I like hand motion. Okay, put it a little bit, and they all get mixed up. Right, so they bounce into each other, they move around. Because we talked about with gases, they really love to fill the volume. Okay. Now, what if I take, here's a harder one. Let's take a big box like this. I'm going to cut it down the middle. On one side, I put salt water, and on the other side, I put fresh water. Then I remove the boundary. What happens? Okay. All right. So he said one goes under the other. Let's say that happens. Then what happens? So we still mix it. What? Oh my gosh, can I not keep anything straight anymore? Well, in fact, you can't. So molecular transport means that individual molecules are going to move shit around regardless of whether you want it to. Bouncing around is going to transport stuff to places you don't want it to go. Okay. And this happens due to concentration gradients. So for example, I just give you two examples of concentration gradients, both in mass and in salinity. But of course, it also happens when you think about a force like gravity, right? So you can think about a vertically stratified fluid, and then we can talk about making a perturbation of that and watching it diffuse. Okay. So we talked about that. Yeah, so let's talk about the concentration gradient for a second. So mass flux and heat flux, they look like this. Mass flux is the tricky one, of course, one that most people are not familiar with. And this one, folks have had some familiarity with, if you took stat mech or computational. So what is this describing? Good reading. What is it describing? Take this one. This one people have some familiarity with. Heat. Heat what?
Flow.
Heat flow. How?
Temperature difference.
Temperature difference. Okay. Heat flow, temperature difference. So which part is the temperature difference? Oh, here, T. Good. Okay. And the gradient. What does the operator gradient do?
The direction of the greatest rate of change.
There's a rate of change with respect to space. So this is a spatial derivative of temperature. So looking for temperature differences with respect to space. So if I have one high T and one low T, right, then this value is large. And therefore the heat flux will suck it away, right? So what happens to something that originally looks like this in temperature space? Make that in hand again. Flat, yeah. So this will originally come down. These will go up. And then eventually it'll become uniform. Gradients like to get rid of variation. Okay, so do mass fluxes. We talked about that in an example with both of the boxes. Gets rid of the mass concentration. The difference in masses, high over here, low over here, it'll even out until it's even. Okay, same thing's true of the temperature. Okay. So great, we did it, right? So will this work for velocity? Can we diffuse velocity in the same way? Raise your hand if you want to diffuse velocity the same way. Higher, be more committed to your thought. Do you have a question or no?
No,
All right, raise your hand if you disagree that you can diffuse velocity this way. Yeah, raise your hand if you've never thought about this before in your whole life. Okay, very good, very honest. Okay, so in fact you can't, and it's a subtle difference. What do we talk about with velocity? What kind of quantity is it? It's a vector. Oh shit, what are these? These are scalars. Yeah, no, we can't do that, can we? You can't take a vector quantity and diffuse it. So let's talk about first what will happen here. So this was the temperature at the beginning. Nice and slanty boy, and then it goes tilted until it's even. Yeah.
I was wondering for heat in the textbook, it's like a bolded Q. Does that not mean vector?
Well, so that's what your gradient gives you. Gradient is a vector quantity. It's a vector operator, right?
Yeah.
Yeah.
But you said we couldn't do it with velocity because it's a vector.
Right, because the quantity we're taking the gradient of is a scalar. So to get this, well, yeah, let's be a little. Sorry, folks. Sometimes I'm not so good with what's written on the board, but you should be like that. And these are mass fluxes in each direction, because the gradient operator operates in all of your spatial direction. Okay. All right. So let's talk about velocity. So when you think about velocity, it's a little weird because you have to think about a velocity distribution with respect to space. Okay, so I want you to imagine this value here. Let's imagine that the fluid itself is moving, but it's moving differentially. So as you go up in y, the speed increases like that. Okay. So now let's think about what's really happening here. These particles in the fluid that are moving faster than these particles are going to bump into each other. Okay, they bump into each other, they pull energy from the faster one, and they deposit it in the lower layer. So they pull it along with the slower fluid. So if this fluid up here is moving very quickly, it begins to make this fluid slow down, and this fluid speed up. Okay, until you diffuse, and I'm going to use quotations here because it's not quite diffusion in the same way we think of it, until you diffuse the velocity gradient until it's flat again. This idea, what we're talking about here, is the idea of viscosity. Okay, so how well a fluid does this is how viscous it is. Okay, if a fluid's very inviscous, when I press it up here, it doesn't quickly retreat back to its original form. Does that make sense? Yeah.
So you said it was more viscous happening here?
No. Less viscous. And if I say it wrong and it's different in the book, we'll correct that. But the idea being here is that there is a gradient equation, Newton's law of viscous forces, which I believe is just this. Where did it go? Let's assume for the purposes of ease, we're just going to do something like that. Tau is mu du dy. We're using y here, I believe. Okay. Oops. Good job. So this is the rate of change of one component of the velocity with respect to y. Multiplied by a little something that we haven't defined yet. It's be like a special sauce for each individual fluid. Okay. And this is going to be how how the velocity distribution is changing with respect to height. Okay. Make sense, or did I lose everyone? Yeah.
What were you saying about what tells you how this is?
The special sauce. So this describes here the diffusion of velocity. And this parameter that's in the front is going to be your viscosity. Okay. It's a way of thinking about diffusing velocity. Yeah.
So the better a fluid is, the velocity is less viscous.
The better, sorry, say that again. The better a fluid is at diffusing velocity, the less viscous it is.
Maybe more viscous?
What do we have here? No, I don't think so. So when you think about a more viscous fluid, it's one that is not moving very much, right? So when you think about something like honey, it has higher viscosity than water, right?
But does that make the velocity diffuse better or worse? Really bad.
Yeah. So here's the thing that you're thinking about. When we think about what we're actually talking about here. So take this one here. Think back to our heat equation. This is fixing our heat velocity or our heat transfer. When we had some bell curve, it's diffusing it out rapidly. So imagine that you have some fluid and you apply what you basically are calling a shear to it, pressing it preferentially in one direction and the other. So if this value here is large, then the shear will be larger. So it's able to diffuse more easily into the fluid and pick it up along the way. Okay, this is not going to have the same type of intuitive feel for you that just talking about honey will do, because when we think about the material properties, right, about how they respond under forces, it's actually not intuitive. We saw, for example, that ketchup, when you hit it with a force, it actually changes its material properties, right? How does it respond under those forces is described by this type of Newtonian law. But it's really important to notice something. This is not a real law that is derived from first principles. This is an empirical. So this here, right, describes an ensemble. This, what we use over here, describes what we see, diffusion of things. And then we take a leap into describing fluids that do fit under this and call them Newtonian fluids. And yet, just yesterday or Monday, we talked about a fluid that blatantly disregards this, right? So when we think about how to take what we see in nature and turn it into mathematics, we have to put a lot of stipulations on it. Does that make sense? So only when we're talking about Newtonian fluids do we use this type of format. Yeah.
So the pitch and the oblique would be the non-Newtonian ones?
Well, oblique is definitely non-Newtonian. I don't know if pitch is. I think pitch just has super high viscosity. Yeah. Okay, we're not going to spend forever here. Fluid's weird. Next one. We're just talking about properties of fluids still. We haven't even talked about statics yet. What's this? On the right hand side? What's that thing? It's a bubble?
The raindrop.
Is it a raindrop? Is it glass? Is it frozen?
I think it's good.
I think it's glass.
Okay, raise your hand if it's frozen. Raise your hand if it's glass.
Can I give my answer? Like what?
No, you're stuck forever with the answer. Okay, in fact, what is this? So this is a demonstration of something called circumspection. What? So there are bubbles in here, but it's not itself a bubble. These are bubbles of air inside of a bubble of water. And it's not a raindrop because it lacks what? Yeah, the little cap that it likes to wear on its head when it's being pulled down by gravity. So where is this from? Space. Okay, so this is from the ISS. This is from low gravity environments when they're in free fall. And you can see the effects of surface tension, which is essentially to pull the sphere in towards itself. And interestingly enough, there are forces here that are pulling each of the molecules in. I think they had to rotate this, which is why there is a, yeah. Anything else? What's that? Money? Oh, honey. Sorry, I can only hear from one ear. Yeah, just we have strong surface tension. That wasn't the one I was thinking of. Yeah. An eyeball? I don't know. Like, is an eyeball a fluid?
I can stand on
No, incorrect. Incorrect. A strong surface tension. You've used this hopefully today, if not yesterday.
Okay, so.
Soap. Okay, all right, let's continue.
You can stand.
Class is out of control. All right, wait, what happened to the, oh God. I've lost control. Wait a second. This is no longer working. Did this die? I have no idea. It just like stopped recording, so. I know, it's not a very good, not a very good recorder. Okay, so let me share this again. Okay. Well, we already had to do this, and we know we hate YouTube videos, but they're just so great. So this one here, we're going to talk about surface tension. Have you ever seen a water droplet in slow motion? Yeah, bloop. Good, very good hand motions. I love hand motions in the class because they're very intuitive. And we're just going to speed past the people talking because they're awful. Okay, so what do you think is going to happen here? You'll notice there's some effects of surface tension already. They've overfilled the water glass. Water's just itching to come out, right? But it doesn't do that. Even though it fills past the container, it has a little bulb or bulge on the edge. And that's because there's molecular tension pulling the fluid back down towards itself. We talked about if you have two immiscible fluids, let's say you have air and you have water, it will build a molecular basically net that separates the two of them. Now it's permeable, right? We want to remember that. So we can still get water to evaporate through it. And similarly, we can get oxygen to dissolve into the oceans, or all the fish would die, right? But as a whole, it's just a little net on the top. Okay, so what happens when we drop a water droplet here? It spills over, okay. What is the drop gonna do? As it drops in, it just gets eaten, right? Or does it do something different? It bounces. I see some jiggle hands. Ripple sends ripples out. Okay, these are our predictions, right? What would surprise you? Nothing. Fucking internet's great. Okay. All right, let's try this.
I'll let you know exactly where to let it go.
Yeah.
All right, try and get it just to bounce on the surface.
I hate when I talk. All right, here we go. All right, so here's the first droplet coming off of a tiny, basically a little tube. Okay. And first, the first one goes right in, and then it bounces right back up. Boing.
No way.
And it just sits there until ooh, a little bouncy boy. And then it sits there until boing. So what's happening here?
Oh, what?
It's the tiniest bouncy boy. Right? See how cute. Well, it gets smaller until what? No, not until it never stops. What's happening in each bounce? You have some giant ball. Okay. What's keeping it in a ball shape? We called it surface tension, but what's really happening? We're talking about molecules, right? Yeah, so it's a polar molecule, right? You have an electric repulsion and attraction. And so you reorient all of the molecules in there so that they're trying to grab their friend. Hey, come be part of our fluid. We're the best fluid around. You have two fluids now, one here, they're not immiscible, so they can mix together. One's a ball sitting on top of the other. You have to wait for all of the molecules in there rearrange themselves, because on the exterior, you have one, right? So let's take the spherical ball. It's trying to pull all the water molecules in. So it's either pointing negative or positive to grab that. And the surface tension is doing the same, trying to pull all of its water molecules down in, so they're oppositely repelling each other. Then they rearrange, whoop, they're fine. Make sense? Intuitive. You would have totally guessed that. Yeah.
Have these slides online?
No.
What if I missed the slide?
That's a great question. What would happen if you missed the slides? No, it's not the classmate recording. There's a recording and they're on cannabis.
No, I wasn't on.
The fact is you didn't read the syllabus, so you would know that. You didn't look at Canvas, so you would know that. All right, so let's talk about the last thing we'll talk about with surface tension. So we'll talk about capillary action. So if you look down, well, it's gross. If you look at your hand, like, oh my God, I'm getting so old and veiny. And you think about how blood in your body moves around. It's going through your skin, little capillaries. These are tiny, 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 tiny tubes that blood likes to run through. Okay. It also happens that if you have a long tube and you put it into water, water will just climb up it. Why is that? Well, because there's a little bit of a surface tension grabbing onto the side of the walls, right? And it pulls itself up the wall. Now you can design certain materials that are hydrophobic, and then when you force water into it, it will form a concave down shape. So it'll look like this. If it's like your traditional glass, it'll look like that. And then if it's hydrophobic, it'll look like that. Make sense? So this is actually how plants drink. Trees love this, because it's what makes them alive. In order to get water from the roots where the water lands, all the way up to the top of the tree, to force it up in very, very tiny tubes using capillary action. Now, if you tried to grab, say, thousands of pounds of water and pull them up 370 feet on your own, you'd have a really hard time. And in fact, trees don't do that. There's no system of levers and pulleys that bring the water up. They just make really, really small holes, and then water just on its own says, hey, let's go. Okay. Is this how straws work? No. No. You say yeah?
Okay.
Yeah.
Is that why, like, if you're painting, say, a room and imagine the wall is doing, you have to layer coats because the wall is actually painting it, the way it's supported?
I don't know.
Oh,
Yeah. Great question. How small are capillaries? Let's have a look at this. Okay. So I have my liquid here. Next time you have your liquid, you just look carefully. And you look at the sides. Does it go up like this or is it mostly flat? And I think mine mostly flat, but a little up. Okay, a little bit of surface tension. If you don't have water, I'm not gonna pass my water around because God knows what will happen. But next time you look at water, just move your cup around. I don't trust you yet. All right. Well, this is not how straws work, but great question about capillaries. So in fact, this is what capillaries look like. Okay, so here is your traditional resting fluid, right? And these are all connected at the bottom. So it's the same fluid, they pour it in. And the only thing that's changing is the size of the beaker. And look at how much higher this goes. That's bonkers, right? But here you can even see I wasn't even lying. Look, that's the curvature.
I think they don't have to move, like.
So that is for hydrophobic material. So this would be hydrophilic material, something that likes water.
It happens to both of them.
Well,
Both of them travel up just as high.
no. For this type of material, for example, is interacting with the water wants to climb up it. So that would be either hydrophobic or neutral. Or sorry, hydrophilic or neutral.
Which is hydrophobic, will it not climb up?
It'll look like this. So it'll have to be pushed up against its will. Right? And so it'll form a little bead. So this is the version where the material itself does not want to be in contact with water. And water does not want to be in contact with it. Whereas here, it's like, ooh, I like the water. And so it tries to climb up the wall a little more. Which is this.
But wouldn't it climb up the wall?
Well, sometimes it doesn't have a choice, right? So sometimes you force it up into a tube, even though it doesn't want to be in that tube. Right, yeah, so that would be the left example. That left example. Okay, and of course, people want to do this to make like hydrophobic coated boats. That can move through water more easily. Quite stupid. Okay, let's continue. Let's talk about fluid statics. This is what we have to do before we can even begin to talk about fluid dynamics. Cool part. What does the word gauge pressure mean?
Pressure gauge agreed.
Good. A pressure gauge would read. Straightforward. Word gauge, word pressure. What's absolute pressure?
It's like something subtracted from the gauge pressure.
Okay.
Atmospheric pressure subtracted from pressure reading.
Yeah, so we want to use these together here. The gauge pressure and the absolute pressure, they're telling us two different things. The gauge pressure usually is measured with respect to a reference level, and that reference level is usually absolute. So like you're saying, yeah, if you want to say, let's take our gauge, you're going to set it to standard temperature and pressures at the surface level. That would be your absolute pressure level, and then everything measured after that would be with respect to it. Okay. Okay, so here's a mental conundrum. Yeah. Gauge pressure. Gauge pressure is someone who I just explained it to.
It's based off of the reference pressure.
Right. So for example, if I have a gauge, this is not a gauge, this is a clicker, but imagine that I go to measure it, right? And I currently want to know the pressure in this room. Okay, and I read it off and I say, oh, it's 45 in arbitrary units. Okay, then I go and I climb to the top of a mountain and I read it off and I say, oh, that's 12. Okay, but 45 perhaps was my absolute. And then I go on here, I crank the dial, and now I set everything to 0. So my gauge now reads 0 at 45. Then I walk over here and it's -3. Whatever, I don't know. Bad gauge. Does that make sense? Okay. Where did this come from? Okay. So here's a little mind bender here. I have a fluid at rest. Okay, here's my triangle. There's P2 over this entire length, dx. Remember that a pressure is defined as what two quantities in ratio?
Force over area.
Force over area, okay. So here I have a force applied to an entire length, dx, and a force applied to an entire length, ds, and a force applied to an entire length, dz. Okay. Can you prove for me that P1 equals P2 equals P3? Go into little groups, talk to your friend. Only make one friend today, not all three. Well, you know, make one. Okay, you guys can be 3 friends, but you can be 3 friends, however you want to do it. Four in the back can't be screwed.
Yeah, sweet, because I figured that one of the things coming. Basically, it has to have like, say, the square. Yeah, I mean, basically, you have to take things. Think of another way, it's like, the front.
We need the vertical.
Yeah. Oh,
Like that.
And we're trying to prove it. Yeah, because you were just saying it's gonna be basically the same. So if you want to ask, yeah, yeah.
Okay, raise your hand if you're ready. You ready to explain it? It's gonna be wrong. So much confidence in this man.
There's a lot of confidence in what these do. Let's do it. It's in with the fuck is
Yeah. So on the bottom, we know that P2 is acting over dx. P3 is acting over dz. P1 is acting over ds. Why do P1, P2, P3, why are they all equal to each other?
he is.
Pressure 1 is pressure 2 is pressure 3. Don't tell me, you tell your friend and see if he's wrong.
Like, if you put like all underwater. Yeah, just if this side's smaller, it doesn't mean it's all the amount of pressure, yeah.
You look like pressure.
Huh?
That's not the right area.
What is it right?
So if I drop, let's say you take my phone and I drop it 1,000 meters down, is the pressure higher or lower? Higher. So there's a difference in height. There's a difference in height here, isn't there?
You're saying lower is different pressure than high.
I'm asking you, is it?
Oh, I thought that was like the. Now I. Is this an object like like?
This is a little bit of fluid.
So this is inside. It's good. So is there fluid inside? Is there fluid?
The fluid is everywhere. We're in a fluids class. We're in water right now. We're all swimming fishes.
Yeah.
And we're in a fish class. And in our fish class, okay, we look at this imaginary triangle. And in this imaginary triangle of static water, I want to know why P1, P2. Make sense? The answer is easy, but the reasoning behind it is not what I've heard said yet. You know what class you're in though, right? Okay, good.
And you want and it's similarly here and what's up there. Yes.
Okay, folks, you ready? Okay, what's the explanation? Why is P1 the same as P2, same as P3? Simple explanation.
Not all the
Here's
trig,
the bit.
It's what?
not all the trig, you don't have to trig.
All the trick, there's like a one-word sentence.
One word.
That's inverses are bigger, but area is also bigger.
Sure, we can go with that, but that's not quite what I'm looking for. More straightforward than it's written on the slide. It's at rest. The fluid is at rest, so therefore the net pressures all have to be balanced. Regardless of the fact that they're angling. So what happens? Let's make this dz small, okay? Let's imagine that we shrink this down while keeping the angle constant. As I make this smaller and smaller and smaller, the part of gravity that's pushing down versus the part that's pushing up, they have to be balanced, right? And this piece here, P1, P3, it's getting smaller, but also dz is getting smaller at the same time. Right? So they must be balanced. And so then unfortunately, balanced just because nothing's moving. That's annoying. I hate this class. I thought this was gonna be fun. Okay, so let me ask you a different question. Okay, vertical equilibrium, right? In that example was given by 1.14. Let's write that down. So this is a requirement of vertical equilibrium. Okay. Is that reasonable? So what is the solution? This P is for pressure. This is rho for density. This is G for gravity. Good. Okay. So if I say the change in pressure with depth or with height, depending on how you want to look at it, is due only to the minus density times G. And let's make an assumption here. Let's assume that the density is the same everywhere and that the gravity is the same everywhere. Can you do that integral? Okay, read, what is it? Equals? P. At any distance, C. Is that reasonable? Why? Why is there pressure at different depths? More or less stuff above you. Does it matter how much stuff is below you? Nope. You don't even have access to that information. You only have access to what's above you. Does it matter what the shape of the container is? No. Only matters how much stuff you have above you. That's what's holding you down, because the force here is gravity pushing you down and molecular forces keeping you up, right? Now, you keep adding fluid, you keep adding fluid, you keep adding fluid. What happens eventually? Those molecular forces break down and you get fusion, but we're not talking about that. That's later, okay? Okay. So this one you're gonna have to work on your own. Ready? So no teaming up for this one. The tallest straw. Can we drink water from the oceans while we're in orbit? No. Yes, okay, you're correct, but prove it to me now. Okay, so I'm gonna have a space straw. Okay, and I put the tube all the way down to the water. Okay, and given these numbers, Could you create a perfect vacuum in your mouth? Yes, I'm gonna do that. T equals 0 in my mouth. What's the tallest straw I can drink from? I don't know. You have to write it down.
Oh, okay.
Like a real number. You all have computers in front of you. You can do any conversion you want on Wolfram. This is to see, can I use the stuff that Mateo was saying, or am I actually just listening and not understanding?
What's,
What's GM?
yeah, on the, is GM.
Gram? 1 gram per cubic centimeter? Oh, I guess that should be per cubic centimeter, not per cubic centimeter. Yeah. So G, get rid of the M. I made this problem, there's gonna be some mistakes in it, okay? It'll be fixed when the slides go up. And then everyone will be like, what are you talking about? There's nothing wrong with the slides. You can round here, you can put it into Wolfram, it'll understand. Use Earth's gravity, density of water, 1 bar of atmospheric pressure. Not looking for, a derivation, looking for, do you understand how to use the equations? No? No?
Okay, we're gonna pause it here. I don't have a solution. You can give me the solution on Monday morning. Unless you have an answer. You don't have an answer? Okay, we're gonna leave it as is here. Okay. That's fluid statics. This is your test on fluid statics. Okay. We're gonna move on to classical thermodynamics. So I'm gonna keep throwing stuff at you. Okay. And then we're gonna be able to do stuff that really matters, which is any fluid moving. Because very often fluids, they move. Right? Currently, the only fluid that's not moving is my water. And this is all you can do. That's the hardest problem you can make in fluid statics. Once you start moving, then it becomes interesting, right? Okay. So let's talk about thermodynamics. Who's seen it before? Okay. What is it?
Yeah. Whole bunch of logs and logs. Okay.
Transfer of heat energy to different systems or different.
Very good. So it's the transfer of heat energy. And for history, let's remember that when people were first trying to discover what the fuck heat was, they thought it was a fluid that passed between objects. So they would look at two systems, and just like we think about the transfer of a fluid from one system to the other, they saw it behaving very similarly. They saw that it diffused, like fluids of different salinity do, right? And so they called it thermodynamics because it was the transport of this thing called heat, the fluid that moved between objects. Okay, now we know a little bit better, but for the purposes of what we're going to see, we've been studying thermodynamics for hundreds of years, 200 years, thinking of it in terms of this thermodynamic property. So let's talk about thermodynamic systems for a moment, because we have to use a lot of new words. They're all going to suck, okay? I'm going to get them wrong half the time. So first, a thermodynamic system is a system of matter that exchanges which of these objects? Any of them? Which of these are correct? All of them are correct? Not mass. Okay, very much not mass. Okay, so a thermodynamic system does not exchange mass. Or momentum. Good. Okay, so I needed an extra one so that mass didn't look so out of place. But in fact, it only exchanges heat, energy, and work. How do we define these quantities for ourselves? What's heat? Okay. How would you define that?
Microscopic kinetic energy.
Okay. How is that different from energy?
It's the particles and molecules of the substance. Fast they're going and how many protons they're making.
Okay, so is that energy or heat? Heat is energy, okay. Are heat, energy, and work all the same type of unit? Yeah, they're all in joules. They're the same unit. Okay, but they mean different things. We're gonna find out exactly what they mean. What's work, other than what I'm doing right now? You're not doing work, right? It's super easy to learn. Everyone knows that. What's work?
Like influencing an object with outside forces or vice versa.
Okay, interesting. So this is the first time I've heard about like inside versus outside. Okay, so I'm talking about a thermodynamic system. What does that word mean? System is what, yeah. Right. So for example, I take my Amazon box, right? Okay, and it's a parcel of fluid, for example, and I'm going to call that my system. And I'm going to say that I can't exchange mass. So all of the particles that are in my box, they're going to stay in my box. I don't get to give any particles away, and I don't get to gain any particles. But I can trade heat, I can trade energy, and I can trade work. Okay? And in fact, we have to start thinking about this. We have to think of something called fluid particles. So we're inside of a fluid, and we're gonna subdivide it in our mind. Okay, so imagine that this is the entire whiteboard, that's all fluid, green ocean water. Okay? And inside of the green ocean water, I have some box. Okay? And a little bit later, as the time go on, the box is getting a little wonky. And a little bit later, maybe it hits some other current, and now the box is really wonky. But the box still contains all of the same molecules. Okay? Now, of course, this is idealized. You never track every single particle because there's 10 to the 23 of them, at least. That's too many. But these are going to be our requirements for fluid dynamics. We're going to say they need to contain the same molecules. They need to be large enough that I can define things like pressure, that I can define things like temperature. Okay? But they have to be small enough that the relaxation time is short compared to fluid motion induced thermodynamic changes. Whew, what did you just say? Okay, what does that mean? What's this word here? Relaxation time. That the 7 weeks we just had in between semesters?
How long the system takes to reach equilibrium?
How long the system takes to reach equilibrium. Good. So can we define equilibrium? Yes, okay, good. What is it?
The fluid is static.
When everything's the same. Not at rest, not zero, the same. Equilibrium is you are like your neighbors. So our fluid parcel here, let's say its temperature is 30 degrees, and the nearby water here is 30 degrees. And then we move it over here, and its temperature is 50 degrees, and the nearby water, the temperature is 50 degrees. If I move this fluid parcel over here, and this is now 70 degrees, and the fluid is 65 degrees, it is no longer in equilibrium. So the relaxation time has to be short, such that as I move this particle, it can exchange with everyone around it, right? And we want to do this short compared to fluid motions induced, maybe I should have put that on one word, fluid motion induced thermodynamic changes. So if, for example, this beautiful drawing that I did of a square moving from here to here to here represents this fluid encountering, say, like a B-72 bomber moving at 4 times the speed of sound, that's going to heat up the fluid. Okay? It's not going to be in equilibrium anymore. So we don't get to use the same fun fluid equations that we've used before. We have to use shock equations, which hopefully we'll see in week 14. If I can get to that quickly. Okay, questions? So these are just the rules. We're going to think about fluid particles like this. And they're going to exchange energy, they're going to exchange heat, they're going to exchange work, but they're not going to exchange mass. We're going to follow the same particles, just like we're following them in a reality TV show. Okay? All right. So let's talk about the first law of thermodynamics. What is the first law of thermodynamics? False. What? Nope.
You can't create energy from nothing.
Okay, so you're not wrong. You're just not saying what I want you to say. Okay, let me say this differently. How do we write the first law of thermodynamics traditionally?
So that the total energy of a system is the heat and the
Yes. Yes. This is what I wanted to say. So there is a little caveat to that, which is, of course, that energy needs to come from somewhere. That the internal energy in a system is due only to the fact that work and heat have been applied to it. Right? So for example, we can write it like this. We can write delta Q plus delta W is equal to the change in internal energy. Now, what the fuck did I say here? So these are little letters. And when they're little letters, we talk about them as intrinsic variables. So these are quantities of the parcel of fluid itself on a per molecule basis. Okay. So little delta E would be the average kinetic energy of a particle, whereas delta Q would be the change in heat, and here would be the change in work. Right? So if we use work to do, or if we use heat to do work, the internal energy may or may not change. Right? Maybe your gas heats up, maybe it doesn't. Okay. So which of these are intensive variables, and which of these are extensive variables? Say that again.
The extensive variable.
What does intensive mean again? It sounds like that, but the way we define intensive, as I wrote it on the board, what's the difference between this and say this versus right? So the state here, the whole system, you give it an extensive variable. That's a variable that describes the entire state, such as the temperature of the whole state. Okay, so that would be the temperature of the whole state, capital X. The variables of individual particles, say mean molecular speed or mean molecular weight, small variables, these are the intensive variables here. If I take two objects, say one parcel of gas here and one parcel of gas here, okay, and I add them together, does this change? No, why not?
Individual particles are gonna notice that.
Right, individual particle doesn't know how big the ensemble is. Is this gonna change? Yeah. So if I take equal amounts of some quantity, say a hot gas in my left hand and a hot gas in my right hand, the per particle energies don't change when I add them together. But if I add them together, I get twice as much energy in my left hand than I had in my right hand. Okay. Intensive, extensive. Okay. Delta E, delta E. First law of thermodynamics is that the change in internal energy on the left-hand side, I think, wait, the right-hand side, sorry, is due to the changes in work and the changes. Okay. They're all different. And it matters how you get there. I didn't want to have to do that. Okay. So heat and work appear at the boundary of a system. Internal energy resides within the fluid. That's why they're on different sides. So on this side over here, this is what the internal energy of the system is. This is what I'm exchanging with the reservoir, this bath that I'm sitting in. So I'm a little fluid parcel like I was over there. I'm sitting in the nice green bath of the chalkboard. I'm exchanging heat or work. That makes sense? Okay. Oh, we don't have enough time in my life. So we're gonna come back to this idea. Read the section on classical thermodynamics. And we're gonna do this. We're gonna do the second law of thermodynamics.
We're gonna finish all of one. We should have finished all of one today, but I'm not fast enough talking, so. Any questions?
Do you want us to finish the tall draw and give you answers on class?
Or right now? It's very straightforward. I can do it on the board. What? Okay, well, how'd you get that? Good. Well, now I want to know. Yeah, see what you get. See if you agree with him. So now I can't do it from space? Is that what you're saying? My whole pitch to Elon Musk is right out the window. Any other questions? What?
It showed you, so.
Yeah.
When they change the product.